In this video, we're going to derive the electric field due to a subtended arc. So in this setup right here, we basically have an arc of charge, in which the total charge on our arc is capital Q, and has a radius of r. And the angle that this arc forms from its center, we're going to say is an angle phi. So these are the three things that we're given, and our goal is to figure out the electric field at this point, right? The electric field at the center of the arc. So how do we do that? Well, basically the first thing we're going to do is we're going to assign an x and y axis, because it's going to make this easier for us to make sure we know what we're doing. So for the x-axis, here's how we're going to draw it. All right, we're going to draw it like this. So our x-axis, and it's going to go through our point of interest. Right, that's our x-axis. And our y-axis is, of course, perpendicular to it. So this would be our y-axis going right through. Right, so this is our y-axis. Now, the way that we've assigned our x and y-axis, the way we've drawn our axis, our x-axis, is in such a way that the angles that we've formed here, right, this angle and this angle are the same, right? That's the way that we're drawing the x-axis. And so basically, these two angles are the same, meaning this angle is half of our whole angle. So really, this angle is phi over 2, this angle is phi over 2, right? We basically cut this arc in half. So this is phi over 2, and this angle would also be phi over 2. That's basically the way we're drawing our x-axis, right? And the reason why is because the electric field at this point will only point in the x direction, right? Our electric field is only going to point to the right, right? This would be the direction of our electric field at this point. And the reason why is because our electric field has no vertical component, right? Has no y component. And the reason why is based on the symmetry, right? Based on the symmetry of it, right? If we're basically not literally cutting our charge in half, but we can imagine the x-axis dividing our charge up. Well, if we think about the charge above our x-axis, the vertical component of the electric field due to this charge would point downward, just like that. And for the bottom half of our charge, right, below the x-axis, the vertical component of the electric field would point upward. But since these are basically the same thing, the vertical components will cancel out. And so we're left with the electric field only going in the x direction. And so you can really see how that works. And so that's why we made the x and y axis the way we did. So basically that's the idea. Electric field will only point to the right. So how do we actually figure out what the electric field at this point is? Well, the way we can do it is we can integrate the electric fields due to point charges along our arc. Basically, along our arc, we integrate the electric fields due to point charges. So we're going to say that we have a point charge right here, right? Point charge that we're integrating right here. We're going to call that charge dq, right? And it's a really small amount of length along our arc. And if you remember, arc length, really, we can say it's a really small amount of arc length, so ds, right? It's the idea. Now, basically, the distance from our point of interest to that point charge that we're integrating is this distance right here, which is still the radius of our arc, isn't it? So we don't really have to label it. It's still the radius of our arc. So if we wanted to find the electric field due to this point charge, we know electric field due to a point charge is just kq over r squared. So really it's just k dq divided by r squared, right? The distance to that point charge, which in this case is the radius of our arc. So just over capital R squared. So this right here would be the electric field due to our point charge. So we'll just call that dE, right? So dE would be that electric field. And dE, right, the electric field due to this point charge is going to point in this direction, isn't it? All right, let me show you. Right, this is our point charge. The electric field due to that point charge, it's going to point that way, isn't it? So really, labeling that, dE will point this way. But remember, dE has a vertical component, right? We don't care about the vertical components because the vertical components are going to cancel out. We only care about the horizontal component of our electric field due to the point charge. So really, constructing this, basically we only care about this component of our electric field, right? We only care about the horizontal component, so we only care about the component that goes in the x direction. right? And so that's the only one we care about. And so really, here's what we're going to do. We're going to say that the angle between our between the horizontal component and our electric field, right, due to the point charge, right here, this angle, we're just going to call it theta, right? Basically, if this angle's theta, then this angle also has to be theta. Yeah, by the way, this doesn't look super clear, but this line right here, it should be like in the same direction as that line, right? So that's the idea. And so you can see how these would be vertical angles. So if this angle's theta, then that angle's theta. And so we're going to say the angle between our electric field due to the point charge and the horizontal component of it is theta, right? So this angle would be theta, right? Basically, theta would vary as we integrate this charge along our arc. So theta would vary. Basically, theta is what we're going to denote that as. So basically, we don't care about dE, we care about dEx. So really, this is what we care about. So in order to get dEx, we need to make sure we are looking at the x component of dE. So we have to say dE times the cosine of theta. So really, we got to multiply this by the cosine of theta. So that's really what we have. And so now that we have that, we're ready to figure out what our electric field is, right? We just got to integrate both sides. So integrating both sides, right? When you integrate dEx, you're going to get E, right? So this would be the electric field due to our arc. And so this is what we get. Notice how k is a constant, so we can pull it out. But not only is k a constant, actually let me erase that. Not only k is a constant, but r squared is a constant. So here are our constants. K and r squared are both constants, so we can pull them out of our integral, right? R is just the radius of the arc, it's constant. So really, we get k over r squared times the integral of dq cosine theta, or just cosine theta dq. And so this is what we're left with. And so we can actually pull out r squared. So this is really the integral we have to solve. So how do we do that? Well, here's what we're going to do. First off, when it comes to evaluating electric field problems, well, we like to bring in charge density. In this case, we're dealing with an arc which goes in a line, right? So we're using linear charge density. And if you recall, linear charge density, I'm just going to erase a little bit of this. Linear charge density is basically charge over length, isn't it? So in this case, we think of it as the derivative of charge with respect to length. In this case, the arc length, right? So we could just say it's the derivative of charge with respect to the arc length. In this case, basically, if you take dq, right, that really small amount of charge, and divide it by that really small amount of length, you're going to get the charge density at that point. And since we're assuming that charge density is constant, right, we're assuming an even distribution of charge along our arc, then we could say that charge density is the same thing as the total amount of charge, capital Q, divided by the total arc length of our arc. But what is arc length? If you recall, arc length, let me just write this. This is an important side note since we're dealing with an arc. Basically, if you recall, let's see, where can we write this? We'll just write it right here. When it comes to arc length is equal to the radius times the angle forming that arc, which in this case, it's our angle phi, isn't it? So this would be true. So we're just going to replace s with r phi, right? Or r phi. I always say r phi for some reason. I always pronounce it as phi, even though I'm pretty sure it's phi. So really, this is just r phi. So that's just what that could be written as. But at this point, we're trying to substitute dq for something. So basically, if we were to solve for dq in this equation, we get d cubed is equal to lambda ds. So we're going to substitute dq. Basically, we're substituting dq for lambda ds. So what we get is E is equal to k over capital R squared times the integral, right? We still have cosine theta, but dq is lambda ds. So this is what we have, right? And I think we can erase this. I'm pretty sure you guys understand that to go from dq to lambda ds to just solve for dq. So it's basically the idea. And of course, lambda is a constant, so we can move that out, right? Because even charge distribution, lambda is constant, so we're just going to move this out to the front of our integral, right? So that's what we get. Of course, we still have ds right here. So now that we have that, this is basically the integral we have to evaluate. But this is theta, and s is arc length. So what do? Well, we know how angle and arc length are related, so why don't we relate them? Now, basically the idea is theta and ds are related, right? Basically, if we have this, theta is this, r would be our radius, right? R would be the radius of this arc, theta is the angle of this arc, and this would be, we're going to refer to that as lowercase s, right? Lowercase s would be the angle of this arc. So s is equal to theta r, right? So basically, s equals theta r. Or I'm going to reverse that because we wrote r phi here, so I'm going to write this as r theta, right? Lowercase s is equal to r theta, right? That's basically what we have here, right? But we're looking for ds, not s, right? Well, if we have a really small change in s, right, a really small change in s, the radius will remain constant, but theta will change, so we're left with d theta. So you can see s becomes ds, theta becomes d theta. So you can think of a change in arc length corresponds to a change in that angle. And so, of course, r is constant, so this would work. So we're just going to replace ds with r d theta, right? So E is just k lambda over r squared times the integral of cosine theta, and then ds is just r, right, r d theta. And by the way, notice how we have r over r squared? But really, this is just going to become k lambda, basically k lambda over r, because we do r over r squared, we get 1 over r. So really, that's what we would get there. So we're left with cosine theta d theta. So this is basically the integral that we're left with. The integral of the cosine theta d theta, which is pretty easy. And notice, basically we're integrating with respect to theta. And we're integrating, remember, we're integrating electric fields due to point charges all the way along our arc. So we're integrating from this angle to that angle, right? And basically we're going to say below the x-axis, that's when we have a negative angle, right? And above the x-axis, we have a positive angle. So basically, these two things right here are our bounds of integration, going from negative phi over 2 to positive phi over 2, right? Because we're below the x-axis, negative, then we reach an angle of 0, then positive phi over 2. So basically negative phi over 2 to positive phi over 2. That's basically what we would evaluate. So now we can integrate this, right? And the integral of the cosine of theta is just the sine of theta. And we're going from negative phi over 2 to positive phi over 2. And so now we can perform our substitution. And we know that this is just going to be the sine of phi over 2 minus the sine of negative phi over 2. Now check this out. We can actually rewrite this as the sine of phi over 2 plus the sine of phi over 2. Because really, basically the idea is that the negative sine of the negative phi over 2, well, the negative sine of negative of some angle x, well, if we just have the sine of negative x, right? So the negative of the sine of negative x is the same thing as the negative of the negative sine of x, right? Because the sine of negative x is the negative sine of x, and so you see how this becomes positive. And so really, this just becomes plus the sine of x, or basically plus sine of phi over 2. So we could just rewrite this as plus the sine of phi over 2, right? That's basically the idea of that. And then when we add those together, you can see how it's going to be 2 sine of phi over 2, right? So sine of phi over 2 plus sine of phi over 2 is just 2 sine of phi over 2, right? So 2 sine of phi over 2. And basically, since we have a 2 there, we could really just move our 2 out to the other constants, right? So really we get the 2 right there. So this is what we have, essentially. And basically, we only have one thing left to do. We have to write lambda as q over r phi, right? Because this is what lambda is in terms of the things we were given, right? We were given the charge of our arc, r the radius of our arc, and phi the angle of our arc, right? So that's what we have. And so we just write lambda for what it is. So we have 2k times lambda, which is q over r phi divided by r. and then we have the sine of phi over 2. And then we have just enough room to fit in our answer. The electric field is, all right, simplifying this, we get 2kq over phi r squared times the sine of phi over 2. And there it is. This would be the electric field due to a subtended arc, right? In terms of the charge, radius, and angle of our arc pretty much this is the electric field at the center of the arc, basically. And so this right here is basically what it would be. And yeah, that's pretty much the idea of where it comes from. That's pretty much it.